Good afternoon. So this project is actually part of the collaboration. The project is the LSST Gaia synergy, and the present PI is Gisella Clementini. Okay, I will go quite fast on the first part, the scientific part. Why do we want to study this or to search for white dwarf planets? This is just because the majority of the stars, 95% or so of the stars will end their evolution as a white dwarf. And so it's interesting to know what will happen to the planetary systems. And presently we know almost nothing about them. There are a lot of open questions. First question is if planets or planetary remnants in close orbits are actually there or not, which is the minimum distance to escape engulfment, which is the minimum mass to survive the engulfment, and also if the period gap actually exists or not, and which are its boundaries. What is the period gap is what we expect to find from theory, because depending on initial distance between the planet and the star, it may happen that the planet is close enough so that the tidal effects will dominate evolution, and at the end we'll get a planet very close to the star, if it is massive enough to survive the engulfment. The other possibility is that the planet is distant enough so that the stellar mass loss will dominate evolution, and at the end we will find the planet quite far from the star. So in between these two extreme cases, we expect to find a gap in the orbital periods or orbital distances. This is a real model of this kind of things, and you see on the left part of these four plots, this is the red giant branch expansion, and you see that depending on initial orbital distance, the planet may enter the star envelope, or the orbital distance can increase. This is the same thing for the HGB expansion, and you see, for example, this case with one sun mass and one Earth mass, and if the Earth should have one U distance at the end before the start of the HGB expansion, then it will enter the star. This is a bit more complicated because there are also the thermal pulses here. What we expect for a white dwarf transit, there are two main things. One is that, of course, the white dwarf is a very compact star, so the typical radius is 9,000 kilometers or so. And so even a relatively small planet will produce a very strong transit depth of the order of 50% or so. And the other important point is that the transit duration is very short. So here you see the orbital period in hours, and this is the transit duration in minutes. And you see that this is just the same plot, but zoom in this part with short orbital periods. And you see, for example, that for one solar radius orbital distance, which means about 4 hours, you will have something less than 1 minute transit duration. For 1 day orbital period, you get about 1.5 minutes duration. So this was what we expect to see, and this is what we saw actually 3 years ago from K2 data. This is up to now, it's the only example of white dwarf transit. This is the periodogram from the K2 data, and this is the light curve done from ground-based telescopes with a better sampling, a 5-second sampling. And you see that indeed the transit duration is of the order of a couple of minutes, and the depth also is 40% or so. This very irregular light curve is likely caused by disintegrating planetesimals. And this is an important discovery because it confirms a general scenario which was produced in the last 10 or 15 years. Now we know that about 25 to 45% of the white dwarfs show an excess of metals, metal pollution, which is likely due to asteroidal disruption. And I will explain why this is the current interpretation in the next slides. Moreover, we know that a fraction of this white dwarf with an excess of metal show also a dusty debris disk in the infrared. And some of these also show a gaseous component in the disk. This is the, let's say, the general pictures. So if we do, for example, UV spectroscopy on the white dwarf, we see a lot of metal absorption lines. These are the heavy atom in the atmosphere, but the time to fall down is very short. That's why we think that this must be produced by external material that is falling into the white dwarf. Then, if you observe the star in the infrared, you see this excess due to the debris disk, dusty debris disk. And in some cases, for example, in this particular case, you see also in the optical some emission line of the calcium-2 triplet around 8,000 Armstrong, which is with this double peak shape, which is due to the gaseous component of the disk. The reason why we think that this is produced by asteroid disruption or things like that is that if you look at the diffusion computations, you see that the time to the sinking time is much shorter compared to the cooling time of the white dwarfs. So, for example, for a relatively young white dwarf, the sinking time is less than 1 year. So you should not see anything if this was real metals in the atmosphere. So this must be material that is falling down from outside the star. And it cannot be produced by interstellar medium because it's too rich there are too many metals. And this is why we think that the most likely explanation is that this is produced by the tidal disruption of minor planets of asteroids. And this is just an idea of how much mass fall down into the white dwarf in 1 mega year. And you see that these are all the metal polluted white dwarf. And you see that the peak of the distribution is, corresponds to a medium-sized asteroids, something like 200, 300 kilometers asteroid. And it's very interesting to look at the chemical composition of this material, because if you, these are all the best known metal polluted white dwarfs, and you see that if you put together the oxygen, magnesium, silicon, and iron, you get almost exactly the same composition as the solar system bodies, in particular the Earth. And this is very interesting because it's not possible to do such measurement for the planets in the main sequence, but it's possible to do that for the material in the white dwarf, the white dwarfs. Let's come back to the Kepler-K2 results. Why, with about 500 white dwarfs, just one transit was found? The answer is not difficult, because if you assume that only 1% of the main sequence planets have an orbital period short enough in order to enter the red giant or AGB envelope, and the mass large enough in order to survive the common envelope, and if you have the transit probability is around 0.1, thanks, for an orbital distance of 1 solar radius, then you see already that you need about 1,000 white dwarfs in order to catch one single transit. And this, by the way, is about the number of white dwarfs that will be observed by TESS in 2-minute cadence. So we need larger statistics, this is quite clear, and the larger statistics can be obtained only with Plato. Plato will produce very nice light curves with a very good sampling, but only for a few thousand white dwarfs. So it's something but not really enough for robust statistics. And so the only possibility to get a much larger statistic is LSST, which will observe a few millions of white dwarfs. In particular, it will observe about 10 to the 5 Gaia white dwarfs, the white dwarf found in Gaia DR2, plus another 2-3 new white dwarfs that will be discovered directly by LSST. And for all these stars, there will be about 800 photometric measurements in 10 years at random times. If you assume that, you consider that about the ratio between the orbital period and the transit duration is of the order of 200-300, it means that in average you will get 3-4 measurements that should happen during the transit. This is the Gaia Waldorf sample. This is a recent paper by Gentile Fusillo et al. And they published a catalog of 500,000 objects. And you see that the color here is a measurement of the probability to be a single white dwarf. So this means that actually the blue ones are single white dwarfs, and the green and yellow ones are likely binaries with a white dwarf plus a main sequence component. This is the LSST surveys. And if you combine this plot with the previous one, you get the number of white dwarfs that will fall in the wide fast deep survey. It's about 200,000 objects. And if you selected all those, only those that have a white dwarf, a single white dwarf probability greater than 0.7, and in this case you get about 100,000 objects. I got this number because this number is in good agreement with the theoretical cooling tracks by Bergeron et al. 2011, for example. So you see the red points here, basically. And on the other hand, the fact that the wide fast deep survey does not include the galactic plane is not really a problem in this case, because you lose basically only 3,000 objects, so a small, something like 3% of the stars or so. This is just a recent simulation by these people. You can see the LSST data and simulation in all the bands, and when you put together all the bands together here, you get 3 or 4 points in the transits, which is at least sufficient to confirm that it is a real transit. After that, of course, you will need follow-up observations. This is another paper, recent paper by Lund et al. 2018. Here you see that basically if you want to have an error of the order of 5 sigma detection, which corresponds to 0.1 magnitude, you will find about a few millions white dwarfs with LSST. And this is the number of transits that you expect as a function of the orbital period, and you see that you can have 0, 1, 2, or even more than 2 transits, depending, of course, on the orbital period. Of course, the short orbital periods are the best ones, of course. And by the way, you expect to find the object in this part of the plot. This is even more interesting because you have the histogram of all the 2.7 million white dwarfs brighter than 23. This is the red histogram. These guys here, they assume that every white dwarf has a planet, has a Earth-sized planet, which is certainly optimistic. But in any case, with this assumption, you should be able to recover the blue part of the histogram to find the planet, to detect the planet. In this simulation, they got this number of white dwarfs, and with this number, 1.8 million comes from the wide fast deep survey, while the others are observed at a lower cadence and are mainly in the galactic plane. So for this larger sample of white dwarfs, to have a lower cadence in the galactic plane makes a difference. Conclusions. For the 10 to the 5 Gaia bright white dwarf sample, the proposed cadence is okay. The low cadence on the galactic plane is not a problem because you lose only 3% of the targets or so, which is not much. And for these stars, it makes sense to ask for an alert when a faint photometric point is seen. And actually, I already asked for that. For the larger sample, which is about 3 million of new orders discovered by LSST, the galactic plane lower cadence is not optimal, and we lose about 1 million of objects, so a better cadence would improve the things. And in both cases, it will be very useful to access the single 15-second exposure photometry, because of course if the transit duration is 1 minute, 15 seconds is something, so you would see the difference between the two exposures, and not only the 30-second photometry. And by the way, I already asked Colin about that, and he told me that we will not have the image difference between the two exposures, but at least if we get the difference between the exposure, the 30-second exposure, and how is it called, the standard field, let's say, after that you will get, in any case, the photometry of that single object in the single exposure. So this is already good in this sense for this project. Thank you very much.
Thank you. You have time?
A very quick comment. Thank you, Roberto, because that was exactly at the beginning of the meeting my curiosity. If it is possible to perform image subtraction on pairs. In such a way you can access this kind of science, not only for white dwarf transits, but there are also other aspects of astrophysics that can be accessed by this kind of time scale.
I guess I'll just restate what I was discussing earlier in the coffee break to make sure everyone's clear on what this means, is that when we detect a source in difference imaging, detecting it based on that 30-second exposure, one of the measurements that we do to follow up that detection is to do photometry on the snap number 1 and snap number 2 and report the difference. Yes, force photometry. So we know the position of the source from the combined image, but then we'll be able to tell you, is it rapidly rising, rapidly falling? But we will not difference the two snaps against each other and then go find all the new detections in that intra-snap difference. I think in most cases you'll get all the science you would want out of the system we've proposed, but let me know if it doesn't work.
So actually I wanted to point out a paper that was written by David Thomas and Steve Kahn. David Thomas is Steve Kahn's student and was just pushed on the archive, that is using neural network, deep learning neural networks to do detection of transients in images that are trailed at the sidereal rate. And I think
you mean planetary transits?
Sorry?
Planetary transits?
Say it one more time.
Planet transits?
Any transient.
Transients, okay.
Yes. Any transients in principle, although it was tested with very simple transient forms. This may be of interest for anybody that is looking to see very short duration transients that are difficult to detect in the 15-second snaps or 30-second exposure.
Yeah. I don't know if it could make sense to make a sort of all these things together in a white paper, or in a white, or maybe just to prepare different white papers on each single scientific case. I don't know. But